All right, so today we're going to talk about conditional probability and the Bayes formula, but now we're going to do it from a different approach. Today is the 29th. So conditional probability, we've been talking about it, right? So conditional probability is a probability that you find the probability of an event A occurring given that an event B occurred, right? And the formula is the probability that A intersect B all over the probability of B, right? That's conditional probability. And one thing I want you to notice, just note one thing, that if A and B are independent, then what do you know? Then the probability of A intersect B is equal to the probability of A multiplied by probability of B, right? And if you want to find the probability of A given B, then utilizing the formula, the probability of A intersect B divided by the probability of B, because they're independent, I can write it as the probability of A multiplied by probability of B divided by the probability of B. So the probability of B's, they cancel out. And what are you left with? You're left with the probability of A given B is equal to just the probability of A. And that intuitively should make sense, right? If you have two events, A and B, and they're independent of one another, meaning that one doesn't affect the outcome of the other, then if I want to find the probability of an event occurring, given that that event that they're independent of occurs, it shouldn't matter. So that's why, and mathematically, it comes out to be so. So the probability of A given B, if they're independent, just gives you the probability of A. Okay? So that's what we have for the conditional probability. And then Bayes formula. Bayes formula is pretty interesting. So if the sample space is partitioned, talked about this word partitioned, right? With mutually exclusive events, that's what it means to be partitioned. You have mutually exclusive events, A1, A2, all the way to AN. So you have N mutually exclusive events that when you union them together gives you the sample space. Then the probability of one of them happening given some other event B, this equals the probability of B given AI multiplied by the probability of AI over, and in the denominator, we call this the law of total probability. Okay, so this is the summation of the probability of B given AI, A sub I, multiplied by A sub I. And this goes all the way from I, from 1 through N. I know, let me make this a little smaller. Okay. All right, guys, so this is the key terms for today's class. Just give me 1 second. I'll be right. Hold on. Let me just pause the recording. All right. So does everybody have this? Everybody okay with this? Did everybody get the PDF for those of you who are able to access it? Can you guys see it? Yes, no, maybe so. Maybe. Okay. Maybe saw it. Okay, so now you guys can't see it yet? Okay, that's weird. I thought you should all be able to see it from your CUNY Blackboard. So the next thing, we have a tree diagram, okay? So we've talked, yeah. Yeah, you guys can check it if you want. So the next thing is conditional probability. We're going to be using a tree diagram, okay? So PDF of previous. No, James. It should be the PDF of today's lecture. It should be on CUNY Blackboard by looking at the content section underneath lecture folders. Lecture number 8, you should see the PDF. Exactly the same thing that you see right here on the screen. You should be able to see it. Okay, so I'm giving you a tree diagram. Okay, and you've seen the tree diagrams before, but now we're going to be using probabilities to figure out what the probability is of an event occurring. So usually we draw these tree diagrams as follows, right? We draw these branches, and then this is event A, this is event B. And then given event A occurring, we have the probability of event C and event D occurring. Same thing happens here. Given that B occurs, we have the event that C or D occurs. And these numbers above are the probabilities of those events occurring. So the probability of A is 0.4. The probability of B occurring is 0.6. Now these numbers here, it's not the probability that C occurs. This is actually the probability that C occurs given that A occurred. This is the probability that B occurs, that D occurs, given that A occurs. This is the probability that C occurs, given that B occurs. And this is the probability that D occurs, given that B occurs. Okay. So what I want to find is the probability that C given B occurs. That's the first thing I want to find. And actually given to me immediately. So this is not really too much computation at all. 0.85. Now, what is A intersect B? I want to find a probability that A intersects B. Does anyone see what's the probability that A and B happens? What's the probability that A and B occur at the same time? Well, the idea is that A and B are two mutually exclusive events. If one happens, then the other can't happen. So this is actually 0. So A and B are mutually exclusive. And I think the next one should have been the other way around, or I think it should have been D. Yeah, this should have been D. So that's a little mistake. A mutually exclusive, Daisy, does not mean they add up to 1. Mutually exclusive. What is mutually exclusive? If A and B are mutually exclusive, then the probability that A and B happen is 0. That's what it means. They can't occur together. That's right. But when we talk about partitioning of a sample space, not only are they mutually exclusive events, when you union all those events together, that gives you the sample space, which would mean that the probability of something occurring in that sample space is 1. Okay, so if you have like a partition of a sample space, and you divide up this sample space into regions that are all events, right? And these events here, because of the way it's drawn pictorially, they don't have any overlap. None of these have an overlap. So the intersection is the empty set. But when you union them together, and you put them all together, you get the sample space. So the probability of the union of the mutually exclusive events occurring would be 1 because it makes a sample space. It makes up the whole sample space. Okay, so then what's the probability of D happening given that B happens? Well, it's exactly what's drawn right here, 0.15. Now, what's the probability of C occurring? If you notice, C, there's like 2 branches that have the event C occurring. So how do we get the probability that C occurs? Well, it matters if A occurred or if B occurred, right? So this is when we use the law of total probability. So the probability that C occurs is equal to the probability that C and A occurs plus the probability that C and B occurs. So what's the probability that B and C occur? How would you find that? Well, you find that by finding the probability that C given A occurs multiplied by probability that A occurs. This is a definition of that you can find using the conditional probability, right? From the conditional probability, you can find the probability that A and B occurs, which equals the probability of A given B multiplied by probability of B. Same thing happens here. How do you find the probability of C and A occurring? Well, it's equal to the probability that C given A times the probability that A occurs. And then you do the same exact thing here. The probability that C given B occurs multiplied by the probability that B occurs. Now, what's the probability that C occurring given that A occurred? 0.75. The probability of A occurring is 0.4. The probability that C given B occurs is 0.85. And the probability that B occurs is 0.6. So when you multiply those probabilities up, you get 0.75 times 0.4 plus 0.85 times 0.6. And I get 0.81. So that should be the probability of C occurring. Does that make sense, guys? The probability of C occurring, I needed to multiply these probabilities up. And the probability of this C occurring, I need to multiply these probabilities up. Do you see how the law of total probability makes sense a bit more? I think drawing the tree diagram makes it a bit easier to understand why we multiply and why we add probabilities up. Why are we multiplying these? and these together? And then why are we adding them after we multiply them together? Why are we adding them? Well, because A and B, they're two events that occur that are mutually exclusive to one another. Now, what would be the probability of D happening then? How would I find the probability of D? It would be the same idea, right? What's the probability of D happening? Well, I would have to find the probability of A happening and then D happening, which would be the probability of D given A multiplied by probability of A plus the probability of D given B multiplied by probability of B. And what would that be? That'll be 0.25 multiplied by 0.4 plus 0.15 multiplied by 0.6. So then what do I get when I do that computation? 0.25 times 0.4 plus 0.15 times 0.6. I get 0.19. And what do you notice about that? About these two probabilities? Well, when you add them up, they give you 1. And that shouldn't come to a surprise. Because if C occurs, right, 0.81 times, then what is the complement of C occurring? It would be D, the event D occurring. It's everything that's left over, right? So it would make sense that the complement of C is 1 minus the complement of C, or the probability of C happening. So 1 minus 0.81 would give you 0.19. So we could have also reasoned it that way. But this is how we use a tree diagram. So any questions about using up the tree diagram? Knowing how to use a tree diagram. Any questions? No questions? All right, so let's move on to the next example. And we're going to be using the tree diagram for some of these so we can figure out a new way of approaching the Bayes formula to solve problems. So here's a simple problem here. We have 2 boxes. It contains black and white marbles. The box number 1 contains, Daisy says, is tree diagram only used for mutually exclusive events? Is it only used for mutually exclusive events? No. It's usually used for like independent events. We've used this tree diagram before. But it's not only used for mutually exclusive events. Because the idea is that, for example, A and C aren't mutually exclusive. A and D aren't mutually exclusive, but these are, A and B are. These 2 events are mutually exclusive, but not these. These aren't. Clearly, there aren't. Okay, so box 1 contains 1 black and 1 marble, no problem. And box 2 contains 2 black marbles and 1 white marble. A box is selected at random and the marble is drawn from it at random. What is the probability that the marble is black? Okay, so do you see the nature behind these problems? There are 2 events that occur. Either you select box 1 or box 2. Do you see how those are mutually exclusive events? You can't have box 1 and box 2 at the same time. You either choose one or the other. And then within that box, either 1 or 2, you have 2 different color marbles. Either they're black or white. So the selection of one of them, you can't choose 2 marbles with the different colors, right? You have to choose only 1. So you see there's like 2 layers of mutually exclusivity. The first one is either box 1 or box 2, and the next one is either black or white. So that's why the tree diagram, the bifurcation of those branches, it makes sense to use it. You don't have to, but this is another way to look at it. So let's draw that tree diagram. So either I have box 1 or I have box 2, right? That's the first layer. And then the next layer is what? I either have a black or a white marble. So let's do that. So we have black white, black, white. And the assumption here is that we are selecting a box at random, and we're doing this in a fair manner. So either I have box 1 or box 2. We only have 2 choices for each for selecting a box. So the assumption here is that we have an equal chance. So either I choose 50% of the chance I choose box 1 or 50% of the chance I choose box 2. Okay. Now that we're in box 1, what's the probability of selecting a black marble? Who knows the probability? 0.5, right? That's right, Saring. Thank you. Because I have one black marble, I got one white marble, I have an equal chance of selecting them. And then that goes for the white one as well. Then now that I'm in box 2, what's the probability of me getting a black? And what's the probability of me getting a white? So the probability of me getting a black in box 2, I have 2 black marbles out of a total of 3. So actually this would be 2/3. And I'm going to leave it as a fraction because I'm not going to write it as 0.6666 repeated. I'm going to leave it as a fraction. And then what's the probability of me getting a white ball? Well, I have 1 white ball out of 3, right? So it will be 1/3. Do you guys see how I was able to find the probabilities using this tree diagram? So the branches indicate the events, and then the numbers above the branch, they tell me the probabilities of that event occurring. So let's look at part A. Part A is saying, what's the probability that I get a black marble? Black, black. So the probability of me getting a black marble is dependent upon whether box 1 is selected or box 2 is selected. I need to add those probabilities up. So then this would be the probability that I'm black, have a black marble, given that I chose box 1, multiplied by the probability of box 1, plus the probability that I select a black marble, given that I selected box 2, the probability of getting box 2. You see that this is called the law of total probability. The event of selecting a black marble is dependent upon whether you get the box 1 and box 2, and these are mutually exclusive. Every problem that we'll be dealing with in this lecture is structurally identical in this manner and with this regard of mutually exclusive events. These are the events that divvy up the sample space. There is no union, but they make up the whole sample space. Either you choose box 1 or box 2, and that's it. Either you have a black or white marble, and that's all. So then we put the probabilities together. What's the probability that the black given the box 1, 0.5, multiplied by the probability of getting a box 1.5, plus the probability that it's black, the marble is black given it's a box 2, that's 2/3, multiplied by the probability that it's box 2, that's 0.5. So then when you multiply and add these up, you get a fraction 7/12, which is equal to 0.583, and this is repeated. So that's my probability. Okay, 7/12. So you can write that right here. Now, what would be just to right? So then, does anyone have any problems with that? Any questions about that? Is that clear? How do you find the probability of a black marble being selected? Good. Now look at the next question. And the next question is the typical kind of question that you'll see regarding Bayes' formula. So the probability that box 1 was selected given that the marble is white. So Bayes' formula is used for inferential probability. You're making an inference of something that occurred. So the black and white, you can think of it as like the effect, and box 1 and box 2 is like the causes. So this is like the causal of events, right? And this is what happens when you have that event occurring. So usually these events occur first. Box 1, box 2, you do that first, and then it's black or white. But now you're given the effect. One of them is black. Now you get to figure out what's the probability of, given that it's black, that you're making the inference whether it would be box 2. What's the probability of box 2 being the one that it came out of, or box 1 being the one that came out of? So you kind of find the probabilities of something that occurred in the past, given what you have now presently. That's where Bayes' formula comes into play. So we can use the formula, right, that we defined from the beginning and from last class, but let's try to use the tree diagram to make sense of it. So I want to find a probability that, given that it's white marble, I want to know that it's from box 1. So given that it's white, so remember when we talk about conditional probability, that this event here becomes my new sample space. So in a way, we don't worry about this. We don't worry about this. We only worry about this possibility and this possibility. That's why the denominator becomes that whole sum that we saw, right? It becomes the probability that it's white given that I have box 1 multiplied by the probability of box 1 occurring plus the probability that it's white given that it came from box 2 times the probability that I selected box 2. Do you see that? So this number here, it's not just a number. This is the probability that it's white given that I selected box 1. This is the probability that I got box 1. This is equal to the probability that this is box 2. And this is equal to the pardon me, not this one. This is equal to the probability that it's white given that I selected box 2. And that's my dog, guys. Pardon me for that. Mel. Okay, so 5/12. Yeah, I have a dog. Sorry, guys. Oh, good. I'm glad I woke you guys up. Some of you. Yeah, he wakes me up too. All right. So that's the denominator, right? That's the denominator. Now, how about the numerator? The numerator is when we're looking for the probability, right, that it's white given that box 1 occurred. So the probability that it's white given that box 1 occurs, multiplied by probability that box 1 occurs. So you see how this here is also written here, but in the denominator, we're including all the possibilities of getting a white ball. And here we're only dealing with the probability of getting a white ball given that it came from box 1. Does everybody see that? So what is the probability? So Sering, I'm not too sure what you mean by 0.5 and or 5/12. But the probability of it being white given that it's box 1 is 0.5, right? So I'm putting this in the numerator. The probability that it's box 1 is 0.5. In the denominator, we get 0.5 multiplied by 0.5 again, because I'm looking at these things. And then I'm adding the probability that it's white given that it's from box 2, which is a third. And then the probability that's box 2 is 0.5. So when you put this in your calculator, make sure you put the parentheses around the right places. So from here is just a calculator question. So we get 0.5 times 0.5 in the numerator, divided by 0.5 times 0.5 plus 1/3 times 0.5. So what I got was 3/5, or 0.6. Okay, guys, does everyone understand what's going on with the tree diagrams? How this is really Bayes' formula? An example of Bayes' formula utilizing the tree diagram. Does everyone see how the tree diagram works? Does everyone know how to read it? It's okay if you don't. This is the time to ask questions. Not bad? Okay. Can everyone see the access to PDF on CUNY Blackboard? Is everyone seeing it or no? Yes? Okay, good, good, good. I just want to make sure everyone is able to see it. All right, great. So this is how we use a tree diagram for problems such as this. Okay, so part B is a typical problem using Bayes' formula. And in the next example, we'll see something very similar. Okay. Okay. And so you should expect in your homework set, which is up now, a lot of word problems like these. So here we have a chess tournament, and we have a probability of winning a game against half of the players. And half of the players that we're playing against are called experts. And the probability of beating an expert is a 0.3 probability. A quarter of the players are intermediate players, and we have a 0.4 probability of beating those intermediate players. And the remaining quarter of them, so we have a chess tournament, half of them are experts, a quarter of them are intermediate players, and a quarter of them are beginners. And we have a 50-50% chance of beating those players. So the question first becomes, what is the probability of just winning a match? So how do we go about doing this? Well, tree diagram. So let's draw a tree diagram. So the first ramification, the first the spreading of these branches first, the first layer of them is whether they're an expert, intermediate, or beginner. Right? We can't play a player that's both an expert and an intermediate. So this is the first layer of having mutually exclusive events. So in this case, we have 3. In the other 2 cases we've been dealing with, we've just been doing 2 branches, right? Every time. This is okay. It happens. We can have more than 2. In this case, we have 3. Now for each of these events, I either win or lose, right? So I'm going to use W and L for that. So I either win or lose. I either win or lose. I either win or lose. So what's the probability of me playing an expert? Well, half of them are experts. So that's why I have a 0.5 probability of playing an expert. Does everyone see that? What's the probability of me playing an intermediate player? Well, a fourth of them, right, are intermediate. So I get 0.25. What's the probability of me playing a beginner? We'll have 0.25 of them, because there's also a quarter of them, right? So the first probabilities is me playing one of the players, right? So either I play an expert, either I play an intermediate, or I play a beginner. Now, given that I played an expert, what's the probability of me winning? So this number here is 0.3. And this is the probability of winning given that I played an expert. Do you guys see that now? What's the probability of me losing given that I played an expert? Exactly, Saring, that's right. It's going to be 1 minus 0.3. Do you see that? And then intermediate, what's the probability of me winning given that it's intermediate? Well, it tells me I have 0.4 chance. What's the probability of me losing? 0.6 chance, right, of probability. What's the probability of me winning given that I played a beginner? Well, I have 0.5, right? And then what's the probability of me losing given that I played a beginner? I got 0.5. Does everyone see that? How we just divvied up the probabilities given the branches, given the certain circumstances of playing an expert, intermediate, or a beginner, and winning or losing. Now, part A only asks me, what's the probability of me winning? I want to know what's the probability of me winning. So to win, I can either have played an expert, I can have played an intermediate player, or I could have played a beginner. So that is why I need to account for this whole branch here. This is one event occurring, or this event could have occurred, or this event could have occurred. Do you guys see how we had to multiply these two? Because this affects this outcome, right? And then I have to add these products, and these products together. And that's why we have this law of total probability. That's where it comes from. That's one way to illustrate it. So the probability of me winning, given that I played an expert, multiplied by the probability of playing an expert, plus the probability that I won, given that I had an intermediate player, multiplied by the probability that I actually get the intermediate player, plus the probability of me winning, given that it's a beginner, times the probability of getting a beginner. Are you guys understanding now? I hope so. The law of total probability. That's what's happening every single time that you use this idea of Bayes' formula. You're really utilizing the law of total probability every time. So then this is 0.3 multiplied by 0.5 plus 0.4 multiplied by 0.25 plus 0.5 multiplied by 0.25. Okay, and so when you put that in your calculator and you compute everything, so you get 0.3 times 0.5 plus 0.4 times 0.25 plus 0.5 times 0.25. And that's right, you do get 3/8, which is equal to 0.375. Okay, so that's the probability of me winning. I have a 37.5% chance. You can write this as a percentage as well. But that's the likelihood of me winning a game, just winning. Now look at the next question, part B. So part A is a total probability question, law of total probability question. And part B is a Bayes formula question. Now it's saying, what's the probability that, given that you won the match, what's the probability that that person that you played was an expert? So then you're like, oh, what does that mean? So I want to find a probability that it's an expert given that I won. So of these events, this one, and this one happening, right? That's the probability of me winning. What's the probability that I am here? That it was an expert. Do you guys see now that why this would make sense now? The probability of me winning, given that it is an expert, multiplied by the probability that it is an expert. That's what I want to find. That's my desired outcome, that it's an expert. But then I have to divide by the total probability of me winning. So the bottom here is equal to the probability of me winning, which is exactly what I found, right? I found this in part A already. I already found what the probability of me winning is. It's this entire thing. Normally, you would write this out over here and plug it in here and make this computation in one fell swoop. But we did it in two parts. So I already did the denominator. I already used Bayes' formula, and I already used half of Bayes' formula, which is the law of total probability. So all I have to do now is plug in the numerator, which I also already know how to write, because the probability of me winning given at an expert is 0.3, and the probability of me playing an expert is 0.5. And I'm dividing that by 0.375 because I know the probability of winning. So when I do that now, I get 0.3 times 0.5 divided by 0.375, and that's 0.4. Which is 2/5. So this is 3/8 here and 2/5. So any questions about this question, this problem, utilizing the tree diagram, visualizing now using the tree diagram, the law of total probability, and applying that law of total probability to Bayes' formula. Is that clear? Yes? Okay, great. Good. Good. So let's do some more Bayes' formula stuff. So again, we have this whole idea of this time instead of a box, it's an urn. We have an urn, we have white and black marbles, and we have more now, right? We have now 5 white, 7 black marbles in urn A. We have 3 white and 12 black marbles in urn B. And now we have a flipping a fair coin. So if the outcome is heads, then a marble from urn A is selected. If the outcome is tails, then a marble from urn B is selected. So part A asks, what's the probability of me selecting a white marble? And then what's the part B asks, what's the probability that the marble that what was selected out of urn A, given that it was a white marble? So do you see now the similarities between all of these problems that we've done so far? It's a very almost now, hopefully, a systematic way of identifying, oh, this is the law of total probability. Oh, this is Bayes' formula. So let's look at the tree diagram of this. So either we have urn A or we have urn B, right? And then urn A or urn B, we either have black or white. Again, so black, white, black, white. Now, they just made an additional little, thing about flipping a fair coin. So if I flip a fair coin, if it's heads, select urn A. If I flip a fair coin and it's tails, select urn B. And because it's a coin and it's a fair coin, so either side, heads or tails, occurs at equal chance of occurring, right? So obviously, the probability of me selecting urn A is 0.5. And the probability of me selecting urn B is 0.5, right? So I kind of it didn't tell you off the bat, but it makes it seem as though there's like another layer to this. All right, so we understand the probability of me selecting urn A and urn B. Now, given that I selected urn A, what's the probability of me selecting a black marble? Well, how many black marbles do I have? I got 7, and the total number of marbles in this urn is 12. So the probability should be 7/12. And then for the white one would be 5/12. And now earn B, what do we have? 3 white out of 15, right? Sorry, for black, we have 12 out of 15. So that's going to be 4/5, right? 12 out of 15. And then for a white marble, it's 1/5 of the time. Okay, so here we have our tree diagram that represents every possibility in this probability experiment. Now part A asks, what's the probability of selecting a white marble? So if it's a white marble, then either this event occurs, the white marble comes from the fact that I got it from urn A, or the white marble comes from the fact that I selected it out of urn B. So then again, same thing, right? The probability of it being white, given that it came from urn A, multiplied by probability of getting urn A, then I have to add a probability that it's white, given that it came from urn B, multiply by probability that it gives me urn B, that I got it from urn B. And then put it in, multiply the correct probabilities together. So given that it's white, I got 5/12. Multiply by urn A is 0.5. Plus the probability that white given urn B, that's 1/5, multiply by 0.5. And so when you put that in your calculator correctly, and you multiply the given probabilities and add them, you get some weird number here. This is 37 out of 1/20th, which is approximately or equal to 0.3083 repeated. Does everyone agree with this? 5/12 times that. So again, the probability of me getting a white marble depends upon getting an urn from urn A or from urn B. So that's why we have to do this calculation, and that's why it's known as the law of total probability, because I'm utilizing the fact that urn B and urn A are mutually exclusive events. So that's why I have to add it, and the conditional probability occurs in trying to figure out that both of them occur, right? What is the probability of me being white and me selecting a white marble and selecting urn B? It's this probability, this times this, and probability of me having a white marble coming from urn A is multiplying these two probabilities together. And then if you want to find the probability of it being white overall, then you just add up those probabilities together. So that's part A. And then part B asks, what's the probability that I got it from urn A, given that it was a white marble? So what's the probability of this happening? So how would we approach this? So urn A, okay. So Saren got an answer. So again, the probability of urn A given white is a probability that I have a white marble, given that I got urn A, times the probability of urn A. And I'm dividing this by a probability that it's white. But I already did that in part A. The denominator I already did, 37 out of 120. And then the probability that it's white given that it came from urn A is 5/12 multiplied by 0.5. So when you put that in the calculator, what do you get? You get 5/12 times 0.5 divided by 37 divided by 1/20th. And I do get exactly that. I do get 25 out of 37, which is 0.657, but these numbers here repeat. Okay. Any questions? Does the tree diagram help in understanding Bayes' formula better and law of total probability? Yeah, right. So yeah, I also see that the tree diagram is much like almost clearer. Because if you just use the formula and you don't have a real deeper understanding of the formula, then it's just a formula and it's very easy just to lose track of what's what. But I hope now, given the tree diagram, you see how useful trees are, first of all, and then you see how it's very like systematic, and it kind of follows, right? The whole procedure of me multiplying things and adding things, it follows from the diagram that you see. So that's very helpful. Okay, great. So no questions about this? Okay. So good. So we've been covering Bayes formula, conditional probability, law of total probability with tree diagrams. All right. Now the last one, the last example. So this question was actually given to real medical professionals, and 80% of those people that were given this question got it wrong. So what is this scenario? So we have a test and there's a certain rare disease, right? And they say that this test is 95% accurate. This was a hard problem in the homework. Really? This goes on the homework? I think it's on the next homework. Homework number 5. Or maybe there was something similar to this from the previous homework, but I'm pretty sure this is like something from homework number 5. And it says that if the person, yeah. If a person has a disease, the test results are positive with probability of 0.95, which is just saying that it's accurate 95% of the time. So if you do have the disease and the results, the test result will give you a positive reading or result 95% of the time. If the person doesn't have the disease, the test results are negative with probability 0.95. So again, it's just reiterating the fact that it's 95% correct. So if you have the disease, it's going to be 95% correct at the time. It's going to say that you have the disease. And if you don't have the disease, then 95% of them, those people that don't have the disease, will be told that they don't have the disease. And this rare disease, a random person can have this disease at a probability of 0.001. So that's 0.1%. So it's like saying out of all the population, 0.1% of the whole entire population has the disease. So this is a very rare disease. Very small number of people have it. And the question was, given that the person just tested positive, what is the probability of having it? So see, do you already see how this becomes a tree diagram? Do you see the tree diagram already? So how would you draw this tree diagram? So I've been giving you all the tree diagrams. So can someone tell me what would be like that first layer or the first level of branches, and then what's the next one? Right. So there's several thoughts here. Some say disease or no disease. Some say positive or negative. And some say incorrect or correct. Huh. So those are good, right? Which one comes first? Is it having the disease or not having the disease, or is it the test result? What's usually the first thing? What comes first? Right. It's either having it, the disease or not having the disease, right? That's like before anything. So either I have the disease or I do not have the disease. Right, right. But there's a probability error, right, of those test results being accurate. So then what's the probability of me having the disease given this problem? Well, it's 0.001, right? 0.1%. So again, pardon me for my dog. I don't know what he's looking at. There's nothing outside. There's nothing around. I don't know. He's like overly sensitive, I guess. So 0.001% of the time, right? You have the disease. So then there's a really large percentage of not having the disease, which is what? 0.999, right? 99.9% of the people don't have the disease. Okay. Now what? The next layer should be what? Either you're given a positive result or you're given a negative result. Either you're giving the positive result of not having the disease, right? Either you don't have the disease and they say you do have the disease, it's a positive result, or they give you the correct result. If you don't have the disease, then you have a negative result. Now you have a positive result. What's the probability of getting a positive result if you have the disease? So if I have the disease and I get a positive result, that happens 95%, right, of the time, 0.95. But what's the probability that I have the disease and it comes out negative? We'll see. That's where the error comes into play. And I think you will see that having a 95%, a test being 95% accurate is actually not that good. Even though it sounds good, right? It sounds 95%, oh man, you got it 95% correct. But that 5% can be a problem. And now the same thing happens, right? For no disease, what's the probability of me getting a positive result? Right, it's 0.05. Why is that? Because 95% of the people 95% of the time that you test people that don't have the disease, it will be correct. So then what's the scenario that the test is correct? When is it correct? It's correct when the person has a disease and they receive a positive test result, or when they don't have the disease and they get a negative test result. So these two scenarios here is when the test is accurate. And then you have what are called false positives, right? So this one here is a false positive and false negatives. So we do have problems, right? Same thing with the COVID testing, right? There's a possibility they give you, oh, it's 80% accurate, 90% accurate. So it sounds like it's good, but then sometimes there's that, there's that chance that it's inaccurate. So this is real, this is real life. So the test is inaccurate. And so then our question is, given that the person just tested positive, so he just tested positive, what's the probability that he does have that this person does have the disease? So how do we approach this problem? what do you guys, now that you guys have seen the examples, how do we approach this? Or what formula are we going to be using? Let's start with that. It's known as what formula? Bayes, right? It's Bayes formula. So then how do I approach this now? I want to find a probability that I have the disease given that I have a positive test result. So then either using the formula itself or using the tree diagram, what would be in the numerator? What would be in the numerator? The probability that it's positive, yeah, but we're also missing something. So it's not only the probability that it's positive, right? So the probability that it's positive, but that you have the disease, given that you have the disease. So I want to find a probability that I'm positive, given that I have the disease, multiply the probability that it's positive. Or I should say, actually, no, it's not positive. It's a probability that I have the disease. So it's this one here, right? This is the desired outcome. That I have the disease and it's positive. But I need to divide this by what? The total possibility of me being positive. And now the probability of me being positive includes the probability, the event that I have the disease, or it includes the event that I don't have the disease, right? This becomes my new sample space. I'm only dealing with now the fact that I do have a positive test result. So either it's from the disease or not having the disease. So then this is where the Bayes formula comes into play. This is the Bayes formula. So the numerator is the same. And the denominator is a probability that it's positive, given the disease is in the person, probability that I have the disease, plus the probability that it's positive, yet I don't have disease, no disease, times the probability that I do not have the disease. So what's the probability of me having a positive result due to a disease? 0.95. And I multiply that by 0.001. Whoops, pardon me for that. Whoa. This just went crazy. Okay. And then you got 0.95 multiplied by 0.001 plus the probability that's positive given that I don't have the disease is 0.05 multiplied by probability that I don't have the disease, 0.999. Okay. And now, can anyone tell me what you guys get as your final answer? Did anyone get the final probability? What's the probability that you have the disease given the fact that it's a positive result? And I'm not sure if this will surprise you. The result will surprise you. And you have to be careful how you write it in your calculator. So you know what? Let me help you guys with that. If you guys need help with plugging this into your calculator, I would recommend, for those of you who have TI-84, right? Let me clear that out. So, you can make this into a fraction by using alpha y equals, and then the first option here, n over d, and then you put 0.95 times 0.001. And then in the denominator, you get the same thing, 0.95 times 0.001 plus 0.05 times 0.999. I get 0.018, and if I want to write this in as a fraction, this is the fraction. Yep, you get 19 over 1018 as a fraction in simplest form, and approximately as decimal, this would be 0.0186 dot 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 dot. Okay. So the probability of you having the disease, given that it's tested positive, it's actually really small. So it's like 1.8% of those people that are tested positive actually have the result, actually have the disease. You would think, so most of the people, when they answered this question, they thought it was 95% because of the wording of it, right? So you have to be careful when they give you these percentages, you have to be careful how you interpret them. Does that make sense to you guys? Does that make sense? Like you would think it would be much higher. I also thought it was much higher, like just from an intuitive level, without having to do all this calculation. You would think that the probability of you having the disease, given that you were tested positive and given that this test is 95% accurate, you would think the percentage of people that actually have the disease is much higher than 1.8%. So the reason why this number is so small is a twofold reason. One reason is your test is inaccurate 5% of the time. The other little thing that's in there is that the probability of you having the disease is very tiny. And so because of those two things compounded together, this is the result. So one way to think about this, I might turn the black page now, is considering if you had 100,000 people, okay, and so if you have 100,000 people, how many people would have the disease? And how many people would not have the disease? This is another way to think about it. So if 0.001% of the people have the disease, right? So 0.001, if you multiply that by 100,000, what would you get? You get 100, right? So 100 people have the disease. So if 100 people have the disease, how many people don't have the disease? 99,000, right? 900 people don't have the disease. Now, of those 100 people, how many people will be tested positive? Well, if it's 95% accurate, right? 95 people, right? 95 people have disease and are tested positive. So these are the true positives, right? So then there's 5 people out there in this, of course, experiment that have the disease, but they're tested negative. So these are the false negatives, right? False positives. Pardon. And then of those 99,900 people that don't have the disease, how many people will be tested negative? Well, if you multiply 0.95, there's 94,905 people that will be a true negative, right? They truly don't have the disease and therefore they have a positive, negative result. But then there's 5% of those 99,000 that will be tested positive. Sorry, this will be sorry, this is false negative. This will be negative. And so this will be 4,000. There's 4,995 people that will be tested positive, but they're not really, they don't really have the disease. So the people that we care about in this problem are the people that lie in this region here. Right. And so the reason why is this is an example of how these percentages that you hear, right, they can be misleading. So you have to understand, don't look at just the percentages when people throw things at you. It's to understand the whole like context of the problem. So you have 100,000 people, but the number of people that have the disease is really small. And the inaccuracy, even though it's only 5%, right? Like the bigger this number gets, the more the bigger this number gets, right? So there's a lot more people that become false positive in reference to the amount of people that there are. So it sounds good. 95% sounds good, but how accurate is that? So then of those people that are tested positive, how many actually have the disease? So 95 out of 4,995 plus 95, which is 4,995 plus 95. So 95 people out of a total of 5,090 people. And if you find that, if you calculate this, this is exactly the probability that we discovered. Okay, so it's just a neat little situation that arises a lot in probability and stats with percentages. So you have to be careful what the percentages are. Okay, so Bayes formula at its finest. So I'll stop the recording here.